Hi everyone, in this video I'm going to be taking a look at something called the intersecting chords theorem, or you may also see it as just the chords theorem. And it's an interesting result that we can conclude about the length of chords that intersect in a circle. So to help think about this, it'll be helpful if we can draw a circle. So I'll just get my soccer tape here to draw a circle. I don't actually own a compass, so this is the best way for me to draw my circles. So here we have a circle, and if I draw a line where the end of the line, the 2 points at the end of the line lie on a circle, that's called a chord. So the intersecting chords theorem, unsurprisingly, involves 2 chords that intersect. So I'll just draw another chord. So here's the 2 points of that other chord. And basically, the intersecting chords theorem tells us that if we take this part here, the length of that part, and multiply it by that part, that's going to be equal to the length of this part multiplied by this part. And obviously, kind of trying to refer to that without giving labels is kind of clunky. So the simplest way to kind of state what the theorem says is to give some labels to all these points. So maybe I'll call this point A and this point B. I'll call this C and I'll call this D. And maybe where the 2 chords intersect, maybe I'll just call that I for intersect. And so basically what the theorem states is that the length of AI times the length of ID is equal to the length of BI times the length of IC. And that's a really handy result that can help us if say, we're dealing with various things in circle geometry, particularly if we're trying to work out the lengths of certain lines. Knowing that 2 chords intersect can then help us make use of this result in trying to work out those lengths. So what I'll do in this video is I'm going to prove this theorem to give you the confidence that you can rely on it. And the basic technique I'm going to use is using what we know about triangles. So here in this circle where I've got these 2 chords, there's a whole bunch of triangles I could draw, but the 2 that are going to be most helpful to us are the triangle formed when I draw this line here. I'll just draw it as a dashed line, and this line here. So the solid lines are the chords, the dashed line are just the lines I've added to get these 2 triangles ABI and CDI. And what I'm going to show is that these 2 triangles are similar. And if I can show that these are similar triangles, then their sides must be in proportion, and from there we can get to this conclusion. So I'll just say, let's kind of write out this proof. If I want to prove that the 2 triangles are similar, one way I can do that is to show that all the angles are equal. And where I might start is showing that this angle AIB is equal to this angle CID. And hopefully that's a fairly clear thing to see because they're opposite angles. And because opposite angles are equal, these 2 angles must be equal. So we can start our proof by saying that angle AIB is equal to angle CID because opposite angles are equal. So that's a good start. Now the next set of angles that I'll focus on are this angle here and this angle here. And I'll refer to those as angle BAD and BCD. And I want to refer to these 2 angles in that very specific way because it makes it clear that both of these angles, BAD and BCD, are lying on the same arc, being the arc BD. So if I write angle BAD and angle BCD, well, we can conclude that those angles must be equal because angles on the same arc are equal. And so I've been quite deliberate about saying BAD and BCD, as opposed to, for example, I could have said BAI and ICD, because here, when I write the angles in that specific way, we can see that both of these angles start and end at the same point. So BAD starts at B and ends at D. BCD starts at B and ends at D, and so there we can very clearly see they must be on the same arc because they're starting and ending at the same point of the circle, and so we can make use of that result that angles on the same arc are equal. Now, having shown that 2 out of the 3 angles are equal, then it naturally follows that the third angle must also be equal, because all angles in a triangle add up to 180 degrees. So now we can conclude that angle, maybe I'll call this angle ABI, is equal to angle CDI, because the angle sum of a triangle, specifically the interior angle sum of a triangle, is equal to 180 degrees. So there we have all our interior angles being equal. So now, therefore, we can conclude that triangle ABI is similar to triangle CDI because all congruent angles, I'll say all congruent angles are equal. And therefore, we can conclude that if the two triangles are similar, then all congruent sides are in proportion. And that's the essence of what then will let us get to this result. Because now, if we can just pick a pair of congruent sides, we can say they're going to be in proportion, or in other words, one of the congruent sides divided by another. That ratio will be equal to the equivalent ratio from the other triangle. So in this case, I'm concerned with AI and ID, and I'm concerned with BI and IC. So it makes sense that I'm going to pick these two sides of this triangle and these two of this triangle. So if I start by saying, I'll think about AI. And if I think about, well, what's the ratio of AI over, let's say, BI? So if I say, what's that ratio in this triangle, ABI, so AI on BI, well, that's going to be the same as the ratio of the congruent sides in this triangle. So the key is, well, what are the equivalent sides? Well, side AI here is the side that has both this single line angle and the double line angle. And in this triangle, the side that touches both the single and the double line angles, in terms of the symbols I've used here, that's this line here, IC. So if I want AI up here, I need to write IC. And then similarly, if I'm thinking about BI, that's got the 3 lines and the single line. So the equivalent there is going to be I to D, which is the 3 lines and the single line. So that's going to be down the bottom, ID. So we know those two ratios will be the same because all congruent sides are in proportion. And now, very simple arithmetic, just multiply the denominators up, and we get AI times ID is equal to, I'll bring the BI up, so BI times IC. And that's exactly what the intersecting chords theorem states. So that's as required. Boom! Alright, so that's how you prove the intersecting chords theorem. The proof is fairly simple, just using the rules of similar triangles. But I think that the key thing to take away is that you can make use of this result when working with circles and chords within circles. If you're ever facing a problem where you have to work out the length of something inside a circle, have this theorem in your back pocket because it may prove to be very handy. So hopefully you found that explanation helpful and informative, and tick boom.